Have you ever wished you had a special shield that only lets certain things pass through? Imagine a wall that allows basketballs to go through, but stops tennis balls. That's kind of what a frequency selective surface, or FSS, does for radio waves. These surfaces are a type of metamaterial. Now, metamaterials are not something you'd find growing on a tree. They are engineered materials designed in a lab with properties that you just don't see in nature. Scientists arrange tiny structures, like little metal shapes, in a repeating pattern on a surface. This pattern gives the material its superpowers. It's all about the structure, not the stuff it's made from. These tiny structures can be rings, squares, crosses, or all sorts of other shapes. When a radio wave hits this surface, the pattern interacts with it. Depending on the wave's frequency, think of it as the wave's color or pitch, the FSS will do one of two things. Media group. Frequency analyzer displaying different wave frequencies. Close-up of adjustable radio frequency equipment at stock, distribute _ equally. It will either let the wave pass right through as if it weren't there, or it will reflect it like a mirror. This ability to choose which frequencies get through is what makes them frequency selective. It's like having a very, very smart bouncer for radio waves, deciding who gets into the club and who has to stay outside. So, why is this better than traditional materials? Well, old-school filters were often bulky and fixed. If you built a filter to block a certain radio frequency, that's all it could ever do. It was a one-trick pony. But with FSS, engineers can design surfaces that are thin, lightweight, and sometimes even tunable. This means they can change which frequencies they block or pass on the fly. It's like upgrading from a simple window to a high-tech smart glass that can turn from clear to opaque with the flip of a switch. This flexibility is a game-changer for all sorts of wireless technology. Building antennas and other wireless parts with FSS is also simpler in many ways. Instead of needing complex, chunky components to filter signals, you can just print these special patterns onto a thin sheet of material. This makes the whole device smaller, lighter, and often cheaper to produce. You can think of it like printing a circuit board. The design is all in the pattern, so once you've figured that out, you can make as many as you need. This simplicity opens the door for using these amazing surfaces in everything from your smartphone to giant satellite dishes. Consider this. Antennas are all about sending and receiving signals, like tiny electronic mouths and ears. But sometimes they pick up noise and interference from other devices, which is like trying to have a conversation in a loud, crowded room. This is where FSS comes to the rescue. By placing an FSS screen around an antenna, we can tell it exactly which frequencies to listen to. The FSS acts as a shield, blocking all the unwanted waves, the noise, from ever reaching the antenna. This allows the antenna to focus only on the important signal it's supposed to receive, making the connection clearer and stronger. This selective filtering also helps antennas send signals more efficiently. When an antenna transmits, its signal can sometimes go in directions we don't want it to, wasting energy and potentially interfering with other electronics. By using an FSS, we can create a sort of smart wall that directs the radio waves where they need to go. This focuses the antenna's power, increasing its directivity and gain. Think of it like swapping a bare light bulb for a flashlight. The flashlight uses a reflector to aim all the light in one direction, making it much brighter and more useful. FSS does the same thing for radio waves. This is especially important for ultra-wideband or UWB antennas. These antennas are designed to work across a huge range of frequencies all at once. The challenge is that within that wide range, there are often specific frequencies used by other important services, like Wi-Fi or GPS. You don't want your UWB device to interfere with them. Metamaterials allow us to design an FSS that carves out notches in the antenna's operating range. It's like telling the antenna, you can use all these frequencies except for this one little slice right here. This lets UWB devices be good neighbors in the crowded world of radio waves. Another cool application is in microstrip filters, which are tiny circuits printed on a circuit board that help manage signals inside a device. Traditionally, these filters could be quite large, but by using metamaterial-inspired structures, engineers can create special patterns that are very good at rejecting interference. These patterns can be designed to create a band-stop filter that aggressively blocks a very narrow band of unwanted frequencies. This leads to smaller, more effective filters inside our gadgets, which means the devices themselves can be smaller and work better. It's pretty neat stuff. Let's talk about something called a high impedance surface. or his. It's another amazing trick we can do with metamaterials. Normally, if you place an antenna very close to a metal surface, like the metal case of a phone, it doesn't work well. The metal ground plane messes with the signal, kind of like how putting your hand over your mouth makes it hard to talk. An HIS is a special surface that acts like a perfect magnetic conductor at a specific frequency. When you place an antenna on it, the HIS reflects the radio waves back in a helpful way, perfectly in sync with the waves coming from the antenna itself. This has a huge benefit. You can build antennas that are super thin and low profile. Instead of needing to be a certain distance away from a ground plane, the antenna can lie almost flat against the HIS. This is incredible for designing sleek, compact devices like modern smartphones, wearable tech, or even antennas that can be integrated into the skin of an airplane. The HIS effectively tricks the antenna into thinking it has all the space it needs, even when it's pressed right up against a surface. It's a clever way to bend the rules of physics to our advantage. Now let's take this idea a step further, with something called a Fabry-Pérot cavity antenna. Imagine taking an antenna and putting it between two special surfaces. One surface is the his we just talked about, which acts as a perfect reflector. The other surface is a partially reflective FSS, our magic wall. When the antenna sends out a signal, the waves bounce back and forth between these two surfaces. This creates a resonance where the waves line up and reinforce each other, building up in strength before they escape through the partially reflective FSS. The result is a highly directional, high-gain antenna. All that bouncing and reinforcing focuses the energy into a very narrow, powerful beam, like a laser for radio waves. This is fantastic for applications where you need to send a strong signal over a long distance to a specific target, like in satellite communications or long-range radar systems. And because they are built from flat, layered surfaces, these Fabry-Pérot antennas are relatively simple to manufacture compared to traditional high-gain antennas like bulky satellite dishes. They are powerful yet elegant in their design. So, why do engineers and scientists get so excited about all this technology? It's because these metamaterial-based antennas are paving the way for the next generation of wireless systems. Think about the future. We want faster 6th-generation networks, smarter cars that talk to each other, and an Internet of Things where every device in your home is connected. All of this requires more advanced antennas that are smaller, more efficient, and smarter than what we have today. Metamaterial FSS, HIS, and Fabry-Pérot designs are key ingredients for making that future a reality. They are not just theories, they are practical tools. These technologies allow us to solve long-standing problems in antenna design. The ability to create thin, lightweight, and low-profile antennas means we can integrate them into places we never could before. Imagine windows that double as 5th-generation receivers, or wallpaper that helps boost your home's Wi-Fi signal. By printing these carefully designed patterns onto surfaces, we are essentially turning everyday objects into functional parts of a wireless network. This moves us away from the idea of an antenna as a separate, clunky object and toward a world where wireless capability is seamlessly woven into our environment. Furthermore, the ability to precisely control which frequencies are transmitted and received is crucial for avoiding a traffic jam of signals. As more and more devices go wireless, the airwaves are becoming incredibly crowded. FSS and related technologies act as the ultimate traffic cops, ensuring that every signal stays in its lane and gets to its destination without interference. This precision leads to more reliable connections, faster data speeds, and less wasted energy. It's all about working smarter, not harder, with the limited radio spectrum we have available. Ultimately, unlocking the power of metamaterial antennas is about more than just making better gadgets. It's about pushing the boundaries of what's possible in science and engineering. By understanding how to design materials with properties not found in nature, we open up a whole new toolbox for innovation. From improving medical imaging devices to building next-generation radar systems, the principles behind FSS and HIS will have an impact far beyond our smartphones. The future of wireless communication is not just coming, we are actively building it, one tiny repeating pattern at a time. It's an exciting time to be watching science in action.